picking up where we left off previously with gases, partial pressures of all the gases in a container equals the total pressure of gas in a container. And that total pressure and partial pressures are all related to the moles total and mole fraction total. Mole fraction is a unitless number. I didn't say that last time and probably should have. It's always a proportional, a percentage kind of number, a decimal number where you add up all the mole fractions of each component and you're going to get a total of 1 because it's a fraction of the whole. Mole fraction is a very useful quantity to know and to measure because you can often only measure the total pressure in your chamber, so you need to know how each of the partial pressures contributed to that total pressure. That's our Dalton's law of partial pressures restated there, just like we saw it before. So one of the labs we normally do in person is something like this. We set up a reaction that creates a gaseous product. So here's the equation of KClO3 breaking down into solid KCl and letting off gaseous O2. So we're producing gaseous O2, that little O2 you see, as this flask thing, this test tube, that's what that's called. Excuse me. As this test tube is heated, we create oxygen gas, and then oxygen gas bubbles through the chamber and starts to collect up here. So oxygen gas is being collected, and as it's collected, it displaces the water. So we have this chamber full of water, but as we collect the gaseous product, the gas floats to the top, and you displace water throughout the reaction. So in the end, you have a bottle that has your O2 gas all trapped in it, but there's also water molecules, water vapor in there, because this whole tub is full of water. Water vapor molecules, water molecules in the gaseous state, will also exist in this mixture. So in this bottle that you've collected your gaseous product in, you've got oxygen and water. So the P total in this chamber is going to be the pressure that oxygen is exerting plus the pressure that water is exerting. So if our P total is from these two partial pressures, how do you find out what is the pressure of oxygen gas specifically? You look up the partial pressure of water. There are tables and tables and tables of this data, and here's a table that I pulled from your textbook that has the vapor pressure of water at various temperatures. So at higher temperatures, we have higher vapor pressures of water. Humidity is higher in the summer than the winter. So if we're doing this reaction at room temperature is designated as 25 degrees Celsius. So 23.76 millimeters of mercury is the pressure that water is exerting in here. So I take my P total minus 23.76 millimeters of mercury, and that will tell me the pressure of oxygen gas specifically. So if I do this sort of thing, it's a little bit different but kind of the same. Mixture of helium and neon is collected above water. If partial pressure of helium is this, what's the partial pressure of neon? Well, if it's collected above water, I know my P total is 745, because it told me so. There. I know my P total is composed of the partial pressure of neon plus the partial pressure of helium plus the partial pressure of water. So if you didn't tell when I just clicked that little button, there are definitely water vapor molecules because it's collected over water. So I can do P total minus helium minus water to give the neon pressure that they're asking me for. And looking at my table, 28 falls right in between both of those. So we're going to estimate a little bit, and we could estimate that at 28 Celsius, maybe it would be 28 millimeters of mercury. So I take my 745 minus 368 minus my guesstimate of 28 milliliters of mercury, and I get the partial pressure of neon is 349 millimeters of mercury in this sample. Partial pressures, not that hard. We can do this. A 266 milliliter sample of SO2 was collected over water at 23 Celsius and this much pressure. What's the volume of dry SO2 at STP? Oh, lots of things. So right now, my P total is the pressure of SO2, and it's collected over water, so the pressure of water is also in there. And that's 723 millimeters mercury minus water would tell me my pressure of SO2. My P total is 723, and at 23, there's no real number, but my previous estimate that I have written down is 221.1 millimeters of mercury. I don't remember if I looked that up in a different table or if I just estimated it right there. I don't know. Maybe I did average these numbers and figure out what the 23 would be approximately. I just don't recall. Sorry. So my pressure of SO2 is 701.9 millimeters of mercury. Well, it's asking what's the volume of dry SO2. Dry SO2 meaning without water vapor. So this is now dry SO2. Volume of dry SO2 at STP. STP, that's standard temperature and pressure. That means 0 degrees Celsius and 1 atmosphere. So we're told at a certain temperature, at 23, the pressure is this and the volume is that. But we're being asked what's the volume at a different temperature and pressure. I'm thinking this sounds like that ratio kind of P1V1 over T1 equals P2V2 over T2. You thinking it sounds like that? Yeah, I'm thinking so. Let me clear this up and write some more. So we just discovered that our pressure of dry SO2 was 701.9 millimeters of mercury. We're going to call that P1. And my V1, 266 milliliters. My T1, 23 degrees Celsius. My P2 is 1 atmosphere. And my T2 is 0 degrees Celsius. Okay, now what? Well, some of these need to be converted. We need to get temperature in Kelvin. Definitely need temperature in Kelvin. So that's 273 Kelvin, and 296. I just did that math correctly. 296 Kelvin. And you cannot have pressure in millimeters of mercury and pressure in atmospheres in the same equation. So let's convert this one to 1 atmosphere over 760 millimeters of mercury equals, what do I have this written as? 0.924 atmospheres. So now I've got compatible units. I can do that in volume in liters, milliliters. It doesn't matter. It's going to substitute in my ratio equation regardless. So I got 0.924 atmospheres times 266 milliliters divided by 296 Kelvin is equal to 1 atmosphere, unknown volume at 273 Kelvin. It's a plug and chug, cross multiply, all that kind of stuff. Make sure you can really do the math. Can you really do the math? I really want to make you prove it to me. 226.7 milliliters. Okay, all that's partial pressure and gas relationships, still using ideal gas law kind of things. Two more little nuggets of gas things. The kinetic molecular theory of gases. The kinetic molecular theory says gases can be treated as points. They are tiny things that have a large distance between one molecule and another molecule, so they're considered points. Because of that, we consider them to have negligible volume. They're constantly in motion in random directions, and collisions among them are perfectly elastic. In fact, I should have said prior to now, the pressure of a gas is all because of collisions with the container that's holding the gas. So if a gas molecule collides with a container, the force at which it hits the side of that container helps determine the force over the area. That determines the pressure of the gas. So collisions with the container are all what's responsible for the pressure. More collisions or higher force collisions, higher pressure. Okay, we'll talk more about that. Gas molecules exert neither attractive nor repulsive forces. So you just treat them as perfectly elastic collisions, meaning they bounce off of each other without any change in energy, ideal gases at least. This is the one we'll spend the most time on. The average kinetic energy of the molecules is proportional to the temperature of the gas in kelvins. Any two gases at the same temperature will have the same average kinetic energy. I'm going to say it again. Yes, I'm reading to you, but I'm going to do it again. Any two gases at the same temperature will have the same average kinetic energy. One more time. Any two gases at the same temperature will have the same average kinetic energy. What? Yeah, so kinetic energy, its average kinetic energy. Kinetic energy is defined as 1/2 the mass times the speed squared. So the average kinetic energy of a gas is the mass times the speed squared. Temperature is not a component in that kinetic energy, so any two gases at the same temperature have the same average kinetic energy. I'm not saying they have the same speed, I'm saying they have the same average kinetic energy. We're going to talk some more. So this last point is all about kinetic energy, but one of the components of kinetic energy is speed. So let's talk about the speed distribution of gases, because speed is one of the components in the kinetic energy equation. So this apparatus on the left is something used to measure molecular speeds. So we have an oven that is going to vaporize our sample into a gas, and as that gas exits a slit in the oven, this whole thing rotates, and the molecules, the gas molecules, hit this detector, that thing, as they flow through that little slit in this rotating wheel thing. So what you end up with is a curve. You end up with a detector that has a bunch of dots on it, like this. And it says there are some slow-moving molecules that took a long time from the time they came out of here to when they hit the detector. And there are some fast-moving molecules, which were very rapid with how fast they flew out of there and hit the detector. But the majority of molecules are moving around this average speed. So if you look at the thickness of this tail and that tail, it seems like this tail tapers a bit more than that one. We'll explain. But the bulk is this thing. So one of the take-home messages is, for any given gas, a single particle of that gas is not moving at a known speed. They're all moving at various speeds, but you can find something called the average molecular speed. So this is a speed distribution. There are giant numbers of molecules moving at all kinds of different speeds, but you can look at a speed distribution curve like these. So this is these are three distribution curves for nitrogen gas. It's not different gases, it's nitrogen gas only. The only variable here is temperature. So if I look at this middle curve, I can say that the top of that curve, it's a little bit to the right, maybe there-ish, the top of that curve is the average molecular speed, but the whole area under the curve is all the molecules moving at all the different speeds, but that's the average. So sometimes you will see us talk about the average speed. It's also known as the root mean square speed, RMS, root mean square speed. That tells me the top of that hill speed. So temperature is one of the variables when I calculate the root mean square speed. If this center curve is at 300 Kelvin, if I go to a hotter temperature, higher temperature, I'm going to get a higher speed, right? If I go to a lower temperature, I'm going to get a lower speed. So this curve is at a temperature lower than that one. So these three temperatures are my distribution curves. The area under the curve in each case is approximately the same because the area under the curve is representative of the number of molecules that are traveling that speed. So, almost done. So if I look at the same but different kind of curve, this is 3 different gases, all at the same temperature. So temperature is held constant, but this time I'm changing the molar mass. So I didn't point out in the last slide, but this little italicized M on the bottom, that's molar mass. Molar mass, as it gets bigger, my speed goes down. My average root mean square speed goes down. So if this gas in the middle is nitrogen gas, we just saw that curve on the last one, this gas must be a heavier gas because it has a smaller root mean square speed, while this gas is a lighter gas because it's got a bigger root mean square speed. So when I keep saying root mean square speed, I'm talking about the height of the hump, right at the very top of the hump. All right, 2 more definitions and then we're out of here. Gas diffusion and effusion. Diffusion, gradual mixing of molecules when they come in contact. So why all these came up in crazy order with ridiculous animations, I don't know. This is a picture of diffusion. I have a bottle of ammonia and a bottle of hydrochloric acid, and when I uncap those 2 bottles, ammonia vapors and hydrochloric acid vapors go out into the surrounding area. And when they come in contact, they actually do an acid-base reaction to create ammonium chloride, NH4Cl. So this cloud of dust you see over here is actually ammonium chloride being created in the air due to ammonia vapors and HCl vapors coming in contact. So in the lab, it's really important that you cap your chemicals so that they don't start doing reactions in the gas phase. It's really important that you keep your 2 chemicals separated from each other, or else you might do some gas phase reactions. Not great. Okay. That's diffusion in this picture. Effusion is when a gas is under pressure and it's going to escape. So this could be a balloon that you're holding the neck of, and you let the neck of that balloon go, and those gas molecules fly all over the room, and that balloon deflates. Well, that's effusion. Gas traveling from one thing to another through a little tiny hole. Graham's law of effusion, Graham's law of diffusion, uses this equation, these equations. Diffusion and effusion are different things, but they use the same equation. It says the rate at which the gas escapes is proportional to the molar mass of the gas. Make sure that you know that the rate 1 over rate 2, 1 over 2, is molar mass 2 over molar mass 1. That order is super important. But if you're given time, this T is time 2 over time 1, you keep your 2 and 1 in the ratio that way. So if given a rate, it's 1 over 2. If given a time, it's 2 over 1. Molar mass, let's always keep it at 2 over 1. Make sure that your 2's and 1's coordinate. That's all that really matters. Okay, I'm really done. Stick a pin in it.